Hello everyone. I am going to present our paper titled Hardware-Aware Pilot Decontamination Precoding for Multi-Cell Massive MIMO Systems with Rician-fading. Massive MIMO is the key technology of the 5G wireless network. It provides beamforming gain, spatial multiplexing gain, and spatial diversity gain. In a conventional massive MIMO systems, we have a coherence interval which consists of two phases, a channel estimation phase and a data transmission phase. However, channel estimation phase is fixed and it cannot offer orthogonal pilots to all the users. So this leads to sharing of pilots among users, which leads to pilot contamination. Because of pilot contamination, spectral efficiency is limited and it cannot grow as we increase the antennas to infinity unboundedly. So to combat this effect of pilot contamination, we considered a large-scale fading precoding technique. Now we'll see like why are we considering hardware impaired system. As we know that massive MIMO consists of large number of antennas at the base station, and each base station is having lots of antennas, and all the antennas they are having a dedicated RF chain and an ADC DAC. So for cost effective design, we need to use low cost RF chains and ADC DACs. But however, these are prone to impairments like RF impairments and ADC DAC impairments. We can have all low resolution ADC DACs, but this will reduce SE drastically. So to combat this thing and to avoid this thing, we are proposing a dynamic resolution ADC architecture. The system model that we have considered is a multi-cell massive MIMO systems is such that it consists of L cells with each cell having a base station. And each base station is connected to a central network controller. We considered a Rician-faded channel such that the LOS component is not deterministic. It consists of a phase which denotes the mobility of the user. So LOS component is also not deterministic, and non-LOS, of course, which is non-deterministic. We didn't consider the deterministic LOS, which is not a very good assumption. So it has to be like phase shift has to be there in LOS to account for the mobility of the users. So in the downlink transmission, we consist of a two-layer precoding. The first layer of precoding is done by the central network controller. It consists of all the data symbols. It has a knowledge of all the data symbols. So first layer of precoding is done by the central network controller. The LSFP signal generated by the central network controller is transmitted to the base stations. As we see, the LSFP signal is nothing but the weighted linear combination of the data symbols of the kth user. We can see, and the weight gamma LK is the complex LSFP weight. This is the LSFP coefficient. Gamma is the LSFP coefficient. Now in the second layer of precoding, is basically performed by the base stations to its respective users. When I say respective, that means users of its own cell. So the locally precoded signal transmitted by the each Lth base station is given as this equation 3. This VLK is the LSFP, large scale faded precoded signal, and WLK is the local precoder. Now we'll see how hardware impairments are added. Each antenna will consist of a DAC followed by an RF chain, and an RF chain is connected to the antenna, which is transmitted. After that, signal is transmitted. So first, let's say XL is the signal. XL goes through the DAC. The DAC, since it is not ideal, it will have a distorting effect. So distortion noise will get added as shown, NL DAC. And to the XL, we are multiplying distortion matrix also called as AD. This distortion matrix is alpha times identity when all the antennas are connected to a low resolution, but since we are considering a dynamic, so it will be non-identity matrix. After this thing, after DAC, the signal goes to RF chain, and then after, since RF is also imperfect, I won't say imperfect, it will be like non-ideal. Since RF is also non-ideal, it will further add a distortion noise denoted by eta. After this, the signal is transmitted, and then the RF the input to the UE is denoted by YLK, but because RF is non-ideal, so same thing will happen here. Here also distortion noise will get added and AWGN because of channel, and then the RF output will go to ADC similarly as shown in the base station also. So the effective signal is at the UE is denoted by YADC, which is given as desired signal plus the effective noise. First term as the second term as the name suggests is pilot contamination. So it is because of the sharing of pilot. The third term non-pilot co-channel interference is basically a non-coherent interference. It is caused by all the UEs except the pilot sharing users. And then we have AWGN noise and the remaining four term. They are caused by RF impairments at base station and UE and ADC DAC impairments at base station and UE respectively. So now we'll see the channel estimation because base station has to estimate channel to precode it. Like here the same color uses the same pilot because I have already talked that it is impossible to assign orthogonal pilots. So users are sharing pilots. So base station uses time domain reciprocity for downlink data transmission. But however, as we talked about the phase in the LOS component, base station is unable to estimate phase because phase is like a small scale fading. It changes drastically. Like it is like highly subject to the user movement. So it is kind of a small scale fading only. It changes rapidly. So base station is unable to estimate. Therefore, we are considering a phase unaware channel estimator, which is much more realistic. Now we'll see the channel estimate. So the channel estimate is basically given by H hat. It is an LMMSE based channel estimate and phase unaware also, which is much more realistic assumption. So it is given by equation 9. Now we'll see the local precoder. We have seen large scale fading precoder. Now we have seeing a local precoder design. So the existing precoder is like MR, which is done in most of the works, and also distortion unaware MMSE precoder, which is also shown in a lot of existing works and has shown a lot of improvement. But however, this precoder does not mitigate the effect of hardware impairments. So to mitigate the impact of hardware impairments, we are proposing a distortion aware local precoding scheme. So the distortion aware precoding scheme is given by equation 13 such that V hat is given by this as shown in equation 14. So the basic principle how we derive this thing is that we are considering an uplink downlink duality. We considered uplink downlink duality to come up with V hat which maximizes the signal received. Okay, so now that we have seen V hat, now we will go to achievable SE analysis section. Achievable, as we have already seen that the signal that we have received at the UE consists of a desired signal followed by all the interfering noises such that beamforming uncertainty, PC, pilot contamination, non-coherent interference, DAC noise, then THI noise, RHI noise. RHI is receive hardware impairments, ADC noise, and then AWGN noise. So basically the DS will be our desired signal and rest will be come under noise. So SINR is given by desired signal and noise. And we used Monte Carlo simulations to get SINR and generate the plots. Why? Because DMMSE is very difficult to solve. Like the closed form of DMMSE is very difficult. So that's why we use Monte Carlo simulations. Now the optimal LSFP coefficients that we have considered is obtained by using a optimization. So which we will discuss now. So now the basic problem formulation is shown in P1. So in this problem, we can see that in this we can see that the ratio, this is non-convex. The N is also non-convex and DLK is also non-convex. So and further it is a ratio. So basically the overall P1 is non-convex. So we can't simply solve it. So for that, we are proposing a minorization and maximization algorithm to solve this non-convex objective function. So first step is minorization step. In this step, we considered a surrogate function to lower bound the objective. Here, as we can see, like we have used a surrogate function, not an original function, but a surrogate function which lower bounds. So it's kind of a like tight approximation to that original function. The original function is non-convex. However, the surrogate function that we have come up with is convex. So we can frame it in convex optimization problem. So in the first step, we have considered a minorization step. After we have this convex function, we will maximize it such that we get a convex optimization problem. Now we'll talk about simulation results. The parameters, first we'll discuss the parameters. So we considered the simulation area to be 1 kilometer cross 1 kilometer, and like number of cells is 4, users per cell is 5, and antennas are 100. And the pilot power we have considered is 23 dBm, and dynamic resolution ADC DAC architecture is 1246 bits in equal resolution, equal proportion. And UE resolution is 4 bits, and RF impairments at base station and UE we have considered to be 0.1 and 0.05 respectively. So first we'll see the comparison of LSFP and SLP. So here we can see that we have taken up ideal, low, medium, and high. These four scenarios we have considered. So in ideal case, basically like UE and base station, they all are ideal, and we can see that the LSFP provides significant gains in MR and distortion aware MMSE. However, as we are increasing our impairments to low, medium, and high, the gains offered by LSFP is getting reduced drastically. High, we can see that like the gains that we are getting is 0.23, while the gain that we are getting in distortion aware MMSE is still significant, which is 2.76%. So from this, we can conclude from a design point of view, it is much better to combine LSFP with DMMSE rather than MR precoding. Now we will see distortion aware SLP to distortion unaware LSFP ratio for different hardware impairments. So here we can see that from the plot, we can see that like the distortion SLP to distortion unaware LSFP ratio is like less than 1, which means in low scenario, which means distortion aware SLP performs slightly inferior in low scenarios. However, as we are increasing, distortion aware SLP starts performing better by a good range, good margin in the severe scenario. So from this, we can conclude that as we are increasing hardware impairments, since distortion aware SLP is performing better, so in the scenarios like high and severe, even moderate also, it is much better to use distortion aware SLP rather than distortion unaware LSFP, because the complexity does not justify, the complexity in the LSFP does not justify this much gains. And distortion aware SLP is much more simpler to have it. Now we will see the another plot which will also confirm this fact that what we just talked. So in this plot, basically we are kind of varying ADC DAC resolution at base station and UE, and RF impairments at base station and UE in x-axis and y-axis respectively. So as the hardware impairments level are increased, which is shown by the yellow region, in this region, distortion aware SLP performs better. And when in the black line, we can see distortion aware SLP and LSFP, they performs almost same. And inside it is distortion aware LSFP is only performing better. So from a designer point of view, a designer can select which precoder it should use depending on the hardware impairment regions. So this concludes this presentation. Thanks a lot. Thank you.